Hello. Hello. Good evening and welcome to this live session 4 for the NPTEL course Advanced Thermodynamics and Combustion. This is session 4, and in this session we will be focusing mainly on the content of week 4. In week 4 we have discussed thermodynamic properties and relations among those properties. Okay. In the previous session we had discussion on entropy and exergy, and also some discussion on second law efficiency and some related topics. Okay. So in this session, we will be focusing on thermodynamic properties and relation among those properties. So we have some questions, but before proceeding to questions, I think it will be better if we can have a quick recap. We'll quickly revise few concepts and also some basic concepts which will be required to discuss the content of this of this session. Sorry. Okay. So first of all, the name of topic is thermodynamic properties and relations. So this word property basically means the variables which define the state of the system. Okay. The properties are the variables which defines the state of the system. Okay. So the properties are state function or point function. Okay. And they are independent of path. And they have exact differentials. Okay. So any variable which is not dependent on path, that variable will have exact differential. What is the meaning of exact differential or differential to be starting point? So let us say we have a variable z that is the function of x and y. Okay. Or you can write z is function of x and y, and that function is basically f. Okay. Then the differential of z is written as a small change in z. How there will be some small change in z? Because if there is any change in x and y or in any of these variables, then there will be some change in z. And how much that change in z is, that will depend how much change in x and y is there. Okay. So that is small change in z, that is given by del f by del x. So that is partial derivative of f with respect to x, keeping y constant, times a small change in x, plus del f by del y, that is partial derivative of f or z with respect to y, keeping x constant, times dy, that is small change in y. Okay. So when if you have the expression or the function which gives the relation of z, x and y, then you can find this differential of z. Okay. If you are directly given this differential, dz is equal to some function times dx, Okay, that function m can be the function of x and y plus some function of again x and y times dy. Okay, then if you want to check that whether this differential of z is exact differential or not, then we have a condition. That condition is that partial derivative of m with respect to y, keeping x constant, should be equal to partial derivative of n with respect to x, keeping y constant. Okay, so this is the condition for exactness. Condition for exactness. Okay, so if you apply the same condition for exactness on this particular equation, then what we look at? So this first term, the partial derivative of f with respect to x, this is m, and the partial derivative of f with respect to y, that is n. Okay, so if you apply the same exactness condition, then what we get? We get the partial derivative of m with respect to y, keeping x constant, should be equal to partial derivative of n with respect to x, keeping y constant. Okay, and m and n are what? They are the partial derivative with respect to x and y. Okay, so you can also write del square z. Let us write it one by one. Okay, the partial derivative of y with respect to partial derivative of m, and m is partial derivative of f with respect to x. Okay, this should be equal to partial derivative with respect to x of this partial derivative with respect to y. Okay, so what we have? So we have this del square f by del y del x is equal to del square f, or let us say, let us write z itself. Okay, so partial derivative of z del x del y. Okay, so if the z is the function of x and y, then you can differentiate with respect to x first and then differentiate with y. You will get certain expression, and you can also differentiate with respect to x first and then you can differentiate with respect to y. You will get another expression, and both of those expressions should be equal. Okay, if those both expressions are equal, then we say that this z is having exact differential. Okay, so this is the condition for exactness. Okay, and if this condition is followed, then we say that it has exact differential, or we can say that is path independent, or it is a point function. Okay, so if any quantity that is not dependent on path, that will follow this particular relation. Why it is so? That you can prove yourself, or for at least a special case, what you can do is you can take any quantity z. Okay, so this is our, let us say, xy plane, and there's some quantity z. Okay, z will have some value at this point. Okay, so this is point a. At this point, coordinates are x and y. So and x and y, z will have certain value. Okay, at another point, that is your point b, here the coordinates are, let us say, x plus dx comma y plus dy. Okay, so the coordinates, the x and y values have changed, so the value of z will also be changed. Okay, and this change can take place in many ways. Okay, so there can be many paths. So for example, what you can do is first change x only. Okay, first change x only and then change y. Okay, so this is one path, let us say. And in another way, what you can do is you can change y first and then you can change x. Okay, so there are two paths, two special paths I have considered here. You can make many more paths, but for simplicity I have taken two paths. Okay, so if you are going from point 1 to point b along this path a c b, then you can find the change in z. Okay, so first, what will you do? You will find the value of z at point A, then you will find the value of z at point B, and you find the difference. That difference dz, you can calculate along both these paths, okay, ACB and ADB, okay, and that change, if that is equal along both paths, then you will get that this condition for exactness has to be followed. Okay, how can you do is how can you do that is you can simply use your Taylor series expansion. Okay, in the Taylor series expansion you will get these second order derivatives, and if you impose this condition that change in z should be equal along both of these paths, then you will see that this condition has to be satisfied. Okay, the condition for exactness. Okay, so again I will leave this proof or special case for your practice, and you can do it yourself, and if you get any problem, then we can discuss it in the next problem, but you should try to do it. Okay, okay, so this is the condition for exactness, and we discussed that thermodynamic properties are state function, point functions. They are you know exact, they have exact differentials. So all the thermodynamic properties, for example pressure, let us say the pressure, that can be the function of other variables. Pressure can be the function of volume and temperature. Okay, so you can write the differential for pressure as some function of volume and temperature. So this pressure, so the derivative of pressure can be written as differential partial derivative of P with respect to V at constant temperature times dV plus the partial derivative of pressure with respect to temperature at constant volume. Okay, so this is the differential of P. Now, if you impose the exactness condition, okay, the exactness condition, then what we get is, first we will take the partial derivative of this first equation, sorry, first part with respect to another variable t. Okay, it was first it was with respect to v, then we are taking with respect to t, and that should be equal to partial derivative with respect to v partial derivative. Okay, so you can change the order in which you are doing partial derivatives, and in both conditions you should get the same value. Okay, so this is how we use this exactness condition. Okay, now there are certain uh, quantities. For example, we have internal energy, we have enthalpy, and two more quantities that we have not mentioned till this lecture. They are Helmholtz function and Gibbs function. Okay, so A is our Helmholtz function and G is Gibbs function. You can have different notations in some texts or lectures. It is used as psi or G, but let us use A for the time being. Okay, so internal energy we have from the TdS relation. TdS is equal to du plus PdV, right? This we have, right? So for du, you can write from this particular equation, du is equal to TdS minus PdV, right? And we can use the exactness condition. So what we get is, we can just compare with that in differential of z. So we can use that same condition here. So what we will get is, okay, let us compare first. Okay, so dz is equal to m dx plus n dy. Okay, and m was partial derivative of z with respect to x keeping y constant. Okay, so if you compare with this thing, then what we get is, we get this t is equal to partial derivative of u with respect to uh, s, right, at constant volume. Okay, so this is another relation. Okay, so like that we use some conditions for exactness, and we can compare with this particular equation, and we can get several other relations. Okay, for example, this relation we just got. Okay, similarly we can write for p. You can compare with n, so minus p, that this will be equal to partial derivative of u with respect to v, right, at constant entropy. Okay, So this is just comparing with this particular equation. Okay. Now, if you use the condition for exactness, we have not used the condition for exactness yet. Okay. The condition for exactness was partial derivative of m with respect to the second variable. This should be equal to partial derivative of second part with respect to the first variable. Okay. This was the exactness condition. Okay. So if you use the same condition here, what we get is we get partial derivative of this m is basically t, right? So partial derivative of t with respect to the second variable, that is our uh, v, right, at constant entropy. This should be equal to partial derivative of p, actually minus p, with respect to t, not t, this is the first s. Okay, s at constant v. Okay, so this we got from partial derivative, sorry, exactness condition. Okay, so this we got from exactness condition. Similarly, you can apply exactness condition on other equations. I will not do the whole derivation. I will just write the final equations. Okay, for example, another equation we have, second equation, H equal to TdS plus VdP. Okay, so if you apply the same condition, what we will get? We will get T is equal to dH by ds at constant s, sorry, p. This and another one will get, just comparing with m and n, that will be v is equal to del h by del p at constant s. Okay, just comparing. And if you use the exactness condition, then what we get is del t by del p at constant s, that should be equal to del v by del s at constant p. Okay, similarly for other equations. Okay, this Gibbs and one more function, Helmholtz function, that we had not defined. They are basically they are defined as, this Helmholtz function is defined as u minus ts, and this Gibbs function g is defined as h minus ts. Okay, so similarly for this Gibbs and Helmholtz function also you can write, and the final expression I'm writing, that is del p by del t at constant v, or rather I think I can write once a is equal to u minus ts, and if you just write the derivative, you'll get dA is equal to du minus tds minus dt times s. Okay, so what we get is du, for du we have another expression from here, right? This one, tds minus pdv, tds minus pdv minus tds minus s dt. Okay, this is our dA. So this TDS, they will cancel out each other, and we will left with dA equal to minus PTV minus SDT. Okay, so this is our the final uh, differential for this Helmholtz function. Okay, so so from this function we can get is one, you can get for one you can get by comparing, and another way you can get by using the exactness condition. So that exactness condition one I am writing. So del P by del T at constant v, this should be equal to del s by del v at constant t. Okay, similarly you can write for the another function, that is Gibbs function, g is equal to h minus ts, and you write the differential minus tds minus sdt, and you use the expression for dh, right? Then finally we will get dh is equal to dg equal to vdp minus uh, this sdt. Okay, and if you apply the exactness condition, then you will get, if you apply the exact condition, you will get dv, partial derivative of v with respect to t at constant p, equal to minus partial derivative of S with respect to P at constant temperature. Okay, this we got by using exactness condition. Okay, so these four equations that we have got by using exactness condition. Okay, these four equations, this equation, this equation, this equation, and this equation. Okay, these four equations that we have got, these are called Maxwell's equation. Okay, that has already been discussed in the lecture. Okay, there are a few things that certain quantities are measurable quantities and certain properties are not measurable quantities. Okay, so the measurable quantities are like temperature, pressure, volume, all these things. Okay, and the non-measurable quantities are, or at least those which you cannot measure directly, they are entropy. You cannot measure entropy directly, right? You can calculate the entropy based on your equations, but you cannot directly measure. Enthalpy you cannot directly measure. Gibbs function, Helmholtz function, all these things we cannot directly measure. Okay, and there are few other things like coefficients. Okay, coefficients are whether although you cannot measure them directly because they are the relation among two quantities, and those two quantities you can measure. Okay, so coefficient you can also think they are like directly given by measurable quantities. For example, specific heat. Okay, specific heat. Specific heat we can define in two ways. One is at constant volume, that we call CV, and that is actually partial derivative of U with respect to T at constant volume. Okay, and another one, specific heat at constant pressure, that is Cp, and that is partial derivative of enthalpy with respect to temperature at constant P. Okay, okay, one more thing, that these internal energy, enthalpy, Gibbs function, Helmholtz function, all these quantities are called potentials. Okay, and this temperature, volume, pressure, entropy, these are called our fundamental, properties. Okay, so we want to express everything in terms of our fundamental properties and also in terms of measurable fundamental properties. Okay, so first of all, let us write the CV in terms of the uh, fundamental quantities instead of this U. So how can we write? We can write du is equal to TdS minus PdV. And if you just use this particular, just compare, then what we get? We get this partial derivative of U with respect to S. This will be what? What we can write? We have du is equal to TdS minus PdV. Then what should be partial derivative of U with respect to S at constant volume? Hmm? And partial derivative of U with respect to, let us write this one first. Hello?
Yes, I'm here. The partial analysis do by do is with respect to
We just need to compare this, okay? dz is equal to mdx plus mdy. Okay, so this n is what? M is t here. Okay, dz by del z by del x. Okay, and here we have del u by del s, right? The partial derivative of this quantity with respect to this first variable. So this is what? This is m, and what is m here? This is t, right?
T.
Correct?
Yes.
Okay.
Yes.
You can also write this as del U by del S at constant volume times, okay, this is already this thing, okay. If you can just use chain rule, you can write this as del U by del T at constant volume times del T by del S at constant V. Okay, so this is the same thing actually, del U by del S at constant V. Is this correct? Instead of directly differentiating with respect to S, we first differentiated U with respect to T and then differentiated T with respect to S, right? This is correct.
Yes,
Okay.
sir.
And this thing was equal to T. Okay. This thing was equal to T. And what is this quantity? This first quantity? This first quantity is CV, right?
CV.
This is
Yes, sir.
how we defined CV. Okay. So CV, so what we can write is CV times this del T by del S at constant V is equal to T. Or also you can write CV is equal to T times del S by del T at constant V. Okay.
Yes, sir.
So initially it was U there, it was a potential. Now we have more fundamental quantities there. Okay. Although this entropy is not non-measurable, but at least this is fundamental, not the potential. Okay. Similarly, the same thing we can do for this enthalpy. Okay. And you can use this particular relation dH is equal to TdS plus VdP. Okay. And then you can write T is equal to this dH by del S. Okay. At constant pressure. And you can proceed in the same way. Then you will get Cp is equal to T. Also, you can guess from here. Okay. It was T times del S by del T at constant U. Sorry, constant V.
V.
The Cv was temperature times partial derivative of entropy with respect to temperature at constant volume. So the Cp should be what? Cp should be exactly the same thing, but instead of at constant temperature, it will be at constant pressure. Okay. Del S by del T at constant P. Okay. So these are two coefficients. There are few more coefficients that also very important. We'll quickly define them. Okay. Another one is isothermal compressibility. Why are we defining these? Because these are the relation among the properties. Okay. And that is the objective of uh, this module, the properties and relations among those. Okay, this isothermal compressibility is defined as alpha is equal to, this is how much volume will change if you change the pressure. Okay, and you know that if you increase the pressure, then volume will decrease, so there will be one negative sign, and if you have more volume, then you have more scope for reduction. So just to normalize that, we divide it by volume, and this thing is at constant temperature. Okay. And there is one more coefficient, that is how much volume will change if you change the pressure, that we can call coefficient of thermal expansion. That is beta, how much volume change if you change the temperature, and there will be no negative sign, and again we'll have to divide it by 1 by volume. Okay. And you can take the ratio of these two coefficients, alpha by beta, and you just simplify a little bit. I'm not doing that. Then you will get del T by del P at constant volume. Okay, so this you can try to prove yourself, but we have just defined these quantities because these quantities will be useful later. Okay, I think with this introduction, with this brief recap, we can try to attempt some questions. Okay,
Yes, sir.
so now let's start. We have question number 1. It says in thermodynamics, the point functions provide a the description of the thermodynamic state. Correct. Okay. The point functions or the state functions, they basically provide they define the thermodynamic state. They rely on the concept of exact differentials, right? because they don't depend, they are not dependent on path, so they are exact differential.
Exactly.
Where dz equal to mdx plus mdy, the condition for exactness is strictly this.
Driven by
So
dx and driven by dy, etc. True.
this is right, correct?
Yes, sir.
इसमें बताना क्या true false, so this is true, right?
Yes, sir.
And coming to the next question. Next question says, write the internal. Okay, there are some measurable and non-measurable variables. Okay, that we just discussed. Okay, measurable and non-measurable variables. It is saying the right internal energy, enthalpy, Helmholtz function, and specific Gibbs function in terms of these variables. Okay, we have already written that when we were driving these Maxwell's equations. Okay, so there's no need to write them again. Okay, so if you have any
So
doubt,
we
then
need
we
to.
can write again. Huh?
So we need to write in measurable like in terms of pressure, volume, and temperature, and in non-measurable variables,
No,
we
no,
need
it
to
is
write
not
it.
saying that. It is not saying that you write explicitly in terms of measurable or non or explicitly in non-measurable variables. It is saying that there are two types of variables. Basically, it is pointing towards the fundamental variables. Okay,
Okay.
pressure, volume, temperature, entropy. Okay, the
Yes.
entropy is non-measurable, but these are measurable, and this entropy is non-measurable. So these are actually potentials. Okay, this internal energy, enthalpy, Helmholtz function, these are potentials. Okay, so it is asking write potentials in terms of fundamental properties.
Okay.
Okay, so that we can write. Actually, we have written, then only we derived these Maxwell's equation
Yes, sir.
in terms of fundamental. Okay. Now coming to the next question number 3. It is saying using the specific Gibbs function defined as g is equal to h minus ts, the exactness differential is expressed as dg equal to vdp minus sdt. Apply the criteria for exactness. Which of the following Maxwell equation directly follows? That we have already done, right?
Yes, sir.
Can do it again. G is h minus ts, then dg is dh minus tds minus sdt. Then you use the expression for h, then you get dg equal to vdp minus sdt. Then you use the exactness condition. The exactness condition, if you use, then you'll get the partial derivative of this first term, that is v, partial derivative of v with respect to the second derivative, that is our t at constant pressure. This should be equal to minus partial derivative of s with respect to the first derivative, that is p at constant temperature. Okay, so which option is correct? Third option. Okay, so if you forget the Maxwell equation, any of the Maxwell equation, you can simply derive that. And also there are some tricks to memorize that, but there is one very uh, elegant mathematical method. If we understand that, then we will not even need to memorize any trick. Okay, that I will try to discuss, but if we have the time. Okay,
Yes.
for example, this question number 4, it is saying that the thermodynamic mnemonic square is a visual way to easily express the different form of thermodynamic potentials. According to this square, the natural independent variables for Helmholtz function are.
Uh, just a second.
Helmholtz function
First
was
option is
this Helmholtz
temperature,
function was what? U minus Ts.
volume.
Hmm? And du minus TDS minus SDT. Then du was TDS minus PdV minus TDS minus SDT, and these things cancelled out, and we had this minus PdV minus SDT. So what variables we are left with? We are left with this volume and this temperature, specific volume and temperature. Okay, these are the variables. Okay, जिनका डेरिवेटिव लिया जा रहा है. So we have temperature and specific volume. Okay, so here we have this square. I hope you already know how to use that. That has been described in the lecture. I will not spend much time on that. Yes, because I want to cover a more mathematical way to understand this square. So should we continue? I mean, do that discussion, or we can continue with the questions, because that will take a significant of.
Sir. Yeah, this is already explained in the.
No, not this square. I mean, because there are lot of equations and lot of mathematical identities like cyclic identity, reciprocal rule, all these things. Okay, and many times we don't know what is the order to be followed. Okay, for example, many times you will find the questions, prove this. Okay, you will have certain expression, you will have something on left hand side, on you will have something on right hand side, or they can ask that write all these things in terms of measurable quantities. Then if you read the solution, then it is very clear, okay, all these steps are followed. But if we try to understand that I want to do it myself, then sometimes it is not clear where to start with. Okay, so there is a very elegant mathematical way that we call Jacobians. So if you have studied Jacobians in mathematics, then it becomes very easy, and you don't even need to memorize this square or any thermodynamic square or any trick like that. Okay, so if you are interested, then we can try to discuss that.
Yes, sir.
Okay, so before starting that, I will briefly explain what the Jacobians are. Have you studied the Jacobians?
Yes, sir. I think so.
Okay, so
Jacobian matrix for
right,
CFDs.
Jacobian, right, correct. So we'll quickly have a brief recap. Okay, so let us say you have a function f. Okay, you have a function f, that is the function of x and y. Okay, you have another function a g, that is the function of x and y again. Okay, then the Jacobian is defined as this matrix. This Jacobian matrix is defined as partial derivative of f with respect to x, partial derivative of f with respect to y,
Right.
partial differentiation of g with respect to x, partial differentiation of g with respect to y. Okay,
Right.
so these Jacobians are very useful. Why they are useful? I hope you have already studied in mathematics. If you have not studied, if like there are, you want to change the variables. Okay, for example, you have certain variables and you want to do integration. But if you want to do integration with respect to those particular variables, then it becomes difficult and you use some another variables. For example, if you want to find the area of a circle, if you want to find the area of circle and if you try to integrate this, then it becomes difficult. Then you use polar coordinates. Okay, then to change this whole system into polar coordinates, then we
We
use these
need to use
Jacobians. Okay,
transform.
transformation of coordinates. Okay, so this is Jacobian matrix, and we write that this partial of f and g with respect to x and y, this is the Jacobian of this j. Okay, sorry, Jacobian of f and g with respect to x and y. This is basically determinant of this particular matrix j. Okay, and we write this as simply in these particular round bracket, not round, the square brackets, f comma g divided by x comma y is equal to determinant of this particular matrix. Okay, so we read this as Jacobian of f and g with respect to x and y with respect to x and y. Okay, so Jacobian matrix is basically a linear approximation, best linear approximation of a non-linear transformation. Okay, so for example, you have a example. If I try to do a quick example, let us say f is equal to x square minus y square and g is equal to 2xy. So can you calculate what will be the Jacobian of x, this f and g with respect to x and y? This is very easy, right?
Yes, sir.
So another example, and why we want to use that is, for example, you have certain integration. integration of a function that is function of x and y with respect to x dx comma dy. Okay, this is the integration, and you want to integrate them. But the direct integration may be sometimes difficult. Then what you do, you use another variables. Okay, you use some uh, other variables u and v, and write x and y in terms of u and v. Okay, so you write x as the function of u and v, and y also the function of u and v. Okay, like that you do many times. Okay, correct. For
Yes.
example,
Yes.
you want to find the area of this circle. Okay, and how will you find the area of circle? You first make this elementary area. The area of this particular small element is dx comma dy. Okay,
Integrate it over x and then integrate it
you
over y.
want to integrate it over x and y. Okay, so
With a
first you will
particular
integrate.
boundary.
Yeah, you will integrate this thing first from 0 to
0 to
r. Okay, I mean, what will be the, so
r.
x
Yes.
can vary from this 0 to this radius r. Okay, first you will integrate from 0 to r, and y will vary from minus r square minus x square to r square minus x square and plus. Okay, like that, right?
Yes, sir.
But if you use polar coordinates, then it will become very easy. Okay, you can use x is equal to r cos theta and y is equal to r sin theta. Then you can calculate the Jacobian of this particular x comma y with respect to r comma theta. Okay, one thing I stop in between here. So if you had this function of x and y, and you want to write x in terms of u and v, and y also in terms of u and v, then this integration is transformed in another coordinate system, and in another coordinate system you can write this integration of f, which was the function of x and y, but x and y are the function of u and v now. Okay, okay. Now you will integrate with respect to du and dv, but this will not be equal, right? Because here this dx and dy, but here you have du and dv. Okay, so these integrations will not be equal. There will be a factor, and what is that factor? That is actually a Jacobian. Okay, j, and that j is nothing but the Jacobian of x and y with respect to u and v. Okay, so you will have to multiply this thing with I mean by Jacobian. Okay, so here you can calculate the Jacobian. So you can find the Jacobian matrix. It will become cos theta minus r sin theta. I'm just differentiating x with respect to r. Now I will differentiate r and then theta. Now I will differentiate r sin theta with respect to r first, then it will be sin theta. Then I will differentiate it with respect to theta, r cos theta. So then we will take the determinant of j. Determinant of j will be r cos square theta plus r sin square theta. So it will be r. Okay. So this integration that you want to integrate here.
Is it r square?
No,
it's
r. It is r. It is r, not r square. Cos theta times r cos theta. So
r cos
r
theta.
cos square theta minus of r sin square theta. So that is r. Okay. So this integration that we had written earlier, integration of dx dy, that will become integration of r. This is r is Jacobian and dr d theta. Okay.
Yes.
The r will vary from 0 to r, right?
Yes, sir.
And theta will vary from 0 to
pi.
2 pi. Okay. Then you just integrate this thing. It will be integration of r with respect to r first and then theta. And you just push the limit, then you will get pi r square. Okay.
Yes, sir.
So what I trying to stress on is that Jacobians can make are used while transforming the coordinates. Okay. And
yes, sir.
what are coordinates in thermodynamics? Like coordinates in your coordinate geometry, x comma y, they define a particular point, right?
Yes, sir. For any
So
thermodynamics.
and in thermodynamics, these point functions, they also define a point. That's why they are a point function, and that point is our system. right?
Yes, sir.
So if you want to do transformation, you have a particular expression in, let us say, non-measurable terms, and you want to write that in terms of measurable terms.
Measurable
Okay,
terms.
then what you are doing? You are doing some sort of coordinate transformation, right?
Yes, sir.
So directly or indirectly, these Jacobians will come into the picture. Okay. So if you understand this thing, it is well and good. If you don't understand, but at least the procedure you should understand. Okay.
Yes, sir.
Okay. Now there are certain properties of Jacobians. Like you have properties of differentiation and integration. Similarly, you have the properties of Jacobians. Okay. So how we define Jacobian? Jacobian of f and g, basically partial derivative of f and g with respect to x comma y. That is the Jacobian of f comma g with respect to x comma y. Okay. And that was our matrix. Okay. So first you differentiate with respect to x keeping y constant, then you differentiated x with respect to y keeping x constant, and you are taking the determinant, right? So you are multiplying the diagonal terms and subtracting them. Okay. So del g with respect to y keeping x constant times del g times x keeping y constant, right? This is the definition of Jacobian. Okay. Now coming to the properties. The property, first property, you have the Jacobian of f and g with respect to x and y, that is defined like this. Now if you take the Jacobian of f comma g with respect to x comma g, okay, so the g is coming in the denominator as well as numerator.
Yes, sir.
G is coming in the numerator as well as in the also in the denominator. So this thing is actually, if you put the g in place of y in this particular expression, you will be left with this thing. Okay. Fine. This is not
Yes,
a
sir.
rocket science. You just need to replace y by g. Okay. And you will
Yes,
get this particular expression. Okay. So many times we are having this type of expression, partial derivative of something with respect to another variable at some keeping other some another variable constant. Okay. So those type of expression we can replace by this particular Jacobian expression. Okay. So this is one
this is
property.
what we are using for our thermodynamic system for now, thermodynamic relation.
Ah, yes. So there are some, I mean, properties of Jacobians. They will be useful. So another property is, let us say, f comma g with respect to x comma y, that you can write as, I mean, if you just flip any of the variable, okay, order also matters. Okay, here first you have f and g. If you flip the order, then it will become g comma f x comma y, but a negative sign. Okay.
Yes.
You can also flip the sign of x and y, but again you will get another negative sign. Okay, all these things you can prove. How can you prove? Because this is the defining equation. This is the definition. Okay, this is the definition. So if you want to prove anything, you just use the definition and you will get the relation, the property. Okay, another property, Jacobian of f comma g with respect to x comma y. You can write this thing 1 divided by Jacobian of x comma y with respect to Jacobian of Jacobian of x comma y with respect to f comma g. Okay, I I know I am writing it, I mean, going very fast, but because of shortage of time, if you feel any difficulty in any step, you just stop me and I can slow down. Okay,
Sure.
Jacobian of f comma g with Jacobian of f and g with respect to z and w. This you can write Jacobian of f and g with respect to x
X,
and
Y,
y times Jacobian
X,
of x and y
Z,
with respect
W.
to z comma w. This is another property. Okay. One more property. Jacobian of f and f with respect to x and y. This is 0. Okay.
Yes, sir.
few more properties I will write. For example, what we had dz is equal to mdx, right? We had that, no?
Yes,
We
sir.
had dz is equal to
dx
ndx.
plus dy.
And what was m? M was derivative of z with
Choose
respect to
y.
x at constant y, right? यही
Yes,
था
sir.
ना? और यहाँ पे हमने ये वाली प्रॉपर्टी लिखी है, यहाँ से अगर इसको कंपेयर करेंगे देन व्हाट वी कैन राइट,
Do fy
whatever is constant. See
equal to m.
here g is constant, so g will be repeated in numerator as well as in the denominator. Okay,
Denominator.
and you are taking derivative of f with respect to y, so sorry, derivative of f with respect to x, so there will be f in the numerator and x in the denominator, and what is constant, that will be repeated. Okay, so similarly this thing is z by x and y is repeated. Okay, fine.
Yes.
So same thing you will write here, dz will be equal to Jacobian of z and y with respect to x and y,
Y.
right, times dx plus, now comes the n, so in n this y will be replaced by x simply, right? Fine, this is
Yes.
another equation. Okay, hello.
Yes, sir. Yes, sir.
Now am I leaving anything? I don't think so. Few more properties, they will be just coming directly from this particular lesson. This is cyclic property. Okay, fine. You brought, I mean, this is just this particular equation written in this form,
So this.
correct?
Yes, sir.
Hmm? Hello.
Yes, sir. I'm just looking into the last property.
Okay, and z comma a equal to m x comma a plus n y comma b. So this we had, no,
Yes, sir.
right?
Yes, sir.
So these are some properties, and now we will write the Maxwell equations in terms of these properties.
Okay, sir.
This is very important property, this last one. Okay, if you have some dz equal to m dx plus n dy, that you can write in terms of Jacobian z comma some dummy variable. Okay, some dummy variable a, okay, is equal to m and dx की जगह x and some dummy variable, the same dummy variable, plus n, then dy की जगह y some dummy variable, the same dummy variable. Okay,
Yes.
is that fine?
Yes, sir.
Hello.
हाँ, is this okay?
Yes, sir.
If there is any difficulty, we can just go back and write everything again.
No, sir.
It's just following from here. Okay, we started with this and we reached there. Okay, now writing the thermodynamic properties in terms of, in the form of Jacobian. We will start with potentials. So we had u is equal to, actually du is equal to TdS minus PdV. So what we can write, u comma some dummy variable, any dummy variable, w This will be equal to, now you tell, I will just write T S comma the same W variable minus P V comma the same W variable. Okay.
Yes.
We had H TH is equal to TDS plus VDP. If you write this, then what will we get? H comma some W variable equal to
Yes.
T S the same W variable plus V
into
P the same W variable. Okay. Fine.
yes.
We had this Helmholtz function minus S dt minus PdV. So Helmholtz function, any W variable W minus S T the same W variable minus P V the same W variable. Okay. And we had Gibbs function minus S dt plus VdP. So what will be next?
Minus S.
Minus S
T comma W.
T comma the same W variable plus V
P comma
P comma W. Okay.
yes.
Now let's write Maxwell's equations in Jacobian form. So first Maxwell equation. Del T by del V at constant S is equal to del P by del S at constant V. Okay. So let us write the first part. So how will we write the differentiation of T? So T will be in the numerator with respect to V. So V will be in the denominator with respect to S. Sorry, S is kept constant. So S will be repeated.
This is a constant.
Right? It is kept constant.
Yes.
Is equal to minus
P
minus P in the numerator and
yes,
S in the denominator and V. This will be repeated. Correct?
Yes.
Okay. That's how we defined it. I mean, this was one of the properties, no?
Yes, sir.
Okay.
Yes, sir.
And there was one more property. What was that? That if we flip the sign, if we flip the order, here in the denominator we have V comma S, right? V comma S in the first part, in the denominator. Yes. And in another part we have S comma V in the denominator, right? If we flip the sign of anyone, let us say if we flip the sign of S comma V, so you can write V comma S with a negative sign, right?
Yes, sir.
So these two will cancel out, right? Are you following what I'm saying? Okay, let's write it once.
Yes, sir. Yes, sir. T comma S will be equal to P comma V. Jacobian
P comma
of
V
T comma S
divided by V comma S with it negative will become positive. So
positive.
these things will cancel out. So what will we get? We will be left
Jacobian
with T comma S is equal to P comma V.
P comma V.
Right? So
yes.
this whole Maxwell equation, the first Maxwell equation, is boiled down to just this form. Okay?
Yes, sir.
Okay. How many Maxwell equations were there?
4.
4. And let us see the magic happen. It will be boiled down to just one equation. Now coming to the second equation, del T by del P at constant S is equal to del V by del S at constant P. Use the same thing. T by P S common minus V by S P common. Sorry, P common. Okay.
Yes.
Flip the order of the denominator.
T
Negative sign will be gone, and what will be left? P comma S equal to P comma V, right?
Yes, sir.
Is it
There's
fine?
supposed to be a negative in the second equation. You didn't write the negative sign.
Oh, sorry. This was not supposed to be negative. And okay, fine. We can flip the order of both of numerator and denominator. Okay, so t comma s, the first part, p comma s, we just flip the order of both p comma v
Yes.
and s comma p, right? So two negatives will cancel out each other, right?
Yes.
Now it is fine.
Yeah.
Okay, so these two, sorry, so these two things will cancel out each other, and what we will have, t comma s is equal to p comma
P comma
v. And what we had earlier in the first equation, t comma s is equal to p comma v. Again, what we have, t comma s is equal to p comma v.
P comma V.
We do the same thing for the third Maxwell equation, and you will see that we will have exact same like this thing only. Okay,
Yes.
so v by s comma p. Okay, so just write t, p, and s will be twice, p, s, and p will be twice. Okay, just flip the sign again. So p comma v, this will we will have p comma s, right? So this thing and this thing cancel out. What we have left, we are left with t comma s is equal to p comma v, right? Again the same thing.
So we just repeated the second one, I guess.
What we
Same
repeated?
one. Second one.
Oh, okay, okay. Second one we repeated. Okay, so this is second one. Third one. Third one was entropy. S comma v at constant t is equal to p comma p by partial of pressure with respect to temperature at constant v. So S by v and t will be repeated, p by t and v will be repeated. Okay, just flip the sign. So what we have? Flip
V
the sign of
comma
first
P.
one. Flip the sign of flip. I mean order of flip, first one. This one. So t comma s and t comma v. Fine.
P comma V.
And
P comma
both
V.
of these things will cancel out. So p comma v is
P comma
t
S.
comma s. And same thing goes for the final Maxwell equation. What is the fourth one? Del
Fourth one
S
is
by del P
two
at constant T
T
is equal to minus V by del
V P.
T at constant T. So S by P and T is repeated is equal to minus V by T and again P is repeated. Okay, this there is a negative sign, so you can just write this thing by flipping the order P comma T. So these things will cancel out. Okay, so again we are left with S comma T is equal to, ये कुछ गड़बड़ कर दिया, we should left with, हाँ सही तो है, S comma T is equal to V comma P, right?
Yes, sir.
So we don't need to memorize all these four equations. Okay, and we also don't need to mug up what that square is. Okay, we say that square is making our life easy, but how to make that square, which letter should come at which corner, along which line, along which edge, how we should make the arrows, all these things we are anyway memorizing, right?
Yes, sir.
But this
Detailed
thing
memory.
is not memorization, this is mathematics, right?
Yes, sir.
We didn't made any trick, it is just mathematics, and all those four Maxwell equations are boiled down to this particular equation, and all those Maxwell equations can be derived from this. Okay,
Yes, sir. So
and
for
another
whatever
thing,
Maxwell equation
huh,
we just need to divide it with the same variables.
right,
Then we'll get the
right, just
Maxwell.
reverse engineering, just reverse engineering. Okay,
Yes, sir.
and so everything is terms of Jacobians. Now, okay, we also discussed coefficient. So let us quickly write the coefficient also in terms of Jacobians. So one coefficient was constant heat, sorry, heat capacity at constant volume, CV. So how it was defined? T del S by del uh,
T.
T at constant
V.
constant volume. Okay. So how can we write this? This we can write T times. So S by T, S by T, and V will be repeated. Correct.
Yes, sir.
Similarly, specific heat at constant pressure. This will be what? T del S by del T at constant P. So T S by T, and in the place of V, it will be P. Okay.
Yes, sir.
Right. We have isothermal compressibility. We had alpha is equal to minus 1 by V del Vy by del P at constant temperature. So how will we write? Minus 1 by V and V by P and T will be repeated. Okay. Similarly, we had beta. This was 1 by V del V by del T at constant pressure. Right. So 1 by V by T at constant pressure. Okay. And we also had the ratio. Let's write that as well. So ratio was 1 by V and del V by, no,
So
yes.
V, sir.
Yeah, this first term will cancel out. So we will be left with del T by del P at constant V. So yes, P comma V, P comma V. Okay. So now everything is in terms of Jacobians. Okay.
Yes. Sir, will there be
Now
the negative sign?
in the
Negative sign for alpha by beta. Minus 1 by V, 1 by V.
no, in alpha there was a negative sign, in beta there was no negative sign, because if you increase the temperature, volume will increase.
Yes, sir.
But you if increase the pressure, then volume will decrease. Okay, to compensate that, I mean, whether it is increasing or decreasing. So for that purpose, we has this negative sign. Okay, if you
Slope
increase
is
the pressure, then how much will be the increase in volume? But it is decreasing, so you put a negative sign. Okay.
Hmm.
Hmm. Okay, so now there is some rules. I will quickly write them as well. So first of all, we will write everything in terms of Jacobian. Okay, write everything. Everything means all the derivatives in terms of Jacobians. Okay, fine. We can write that easily, no problem. Then, if there is any thermodynamic potential, okay, if there is any thermodynamic potential, then we will have to use those particular relations that we had for the thermodynamic potentials. Okay, so if thermodynamic potential appears in the expression, then eliminate them using respective relation. Respective relation means, for example, if you encounter dh somewhere, then you will use this particular relation. Dh is equal to tds plus vdp, but you have already written everything in terms of Jacobian, so we'll write dh, sorry, h comma w is dummy variable, is equal to t s comma w plus v p comma w. Okay, so that h will disappear. Okay, so everything will be in terms of our fundamental uh, properties. Okay, so same thing goes for u Helmholtz function, Gibbs function. Okay, that we have already written earlier, so I'm not writing that again. Huh?
Nothing, sir.
Now we want everything to be in terms of measurable properties, right? Or in terms of coefficients, right? Either measurable properties or in terms of coefficient. Now, if S appears, then S can appear with T. If S appear with T means temperature, then we will use the Maxwell equation. Maxwell equation is S comma T is equal to V comma P, right? We will do some examples, then everything will be clear. Okay. So currently I'm doing everything very quickly because we don't have much time. If S
Yes.
appear with P, then use this CP definition. CP was T S comma P
S comma P
divided
T.
by T comma P. Okay. Okay. So now S is with P. Okay. So either like this will be what is S is appearing with T. So this will be S comma T. Okay. So if you encounter anywhere this S comma T, you will use simply instead of S comma T, you will write
V comma
V comma P. Okay. Now if S is coming with P, then now if S is coming with P, then what will you write?
P
CP
comma.
TP by SP, right?
Yes, sir.
Okay.
Sir,
Clear,
can
right?
you go back to the number 2?
Number 2. Yes.
Yes, sir. Yeah, because I got a call at that time. I was
Okay. Okay.
just. Oh, yes, sir. Done.
Okay. So let's do it again. So is S is appearing with P, so we'll get S comma P, something like that. But we have CP is equal to T S comma P by P comma P. So that we can use here. Okay. So as P S comma P, you can replace by what? CP by T and T comma P, right? Like that.
Yes.
And S has come with T, you discussed S with P. Now S can come with V, right? If S comes with V, like you have S comma V, something like that. If you have V comma S, that means minus S comma V. But if they appear, I mean, if S and V they appear together, then we will use what? Definition of CV, right?
Yes, sir.
What was CV? CV was T
T into S
and
comma B by
uh,
T comma B. Jacobian. T comma
right,
S comma T comma.
at constant volume. Okay. And if Jacobian relation contain PTV, then you will use alpha beta or alpha by beta by that. Okay.
Yes, sir.
If Jacobian relation contain PTV, we can use other coefficient alpha beta and alpha by beta.
Sir,
Okay.
will you be sharing this PDF with us again?
Yes, I will share. Okay. But I'm writing very fast, so there may be some things I have not written very detail, but
That
I
is
hope
fine, sir.
okay. And also I'm writing it very fast, so there can be some mistakes, but if you are listening, then you can easily figure out, right?
Yes, sir.
Anyways, now let us say you have a question. Write T del P by del T by del P at constant entropy in terms of measurable. How will we proceed?
Okay, T comma yes.
First, let
T
us
comma.
do without Jacobian. Okay, so we can see, I mean, using both methods. Okay,
Yes.
first of all, we have a cyclic relation del T by del P at constant entropy times del P by del S at constant temperature, del S by del T at constant pressure. This is what? -1. This is our
Minus 1.
cyclic relation, right?
Yes.
Okay. And this particular term, del S by del T at constant pressure is what? That was related to Cp, right?
CP.
That was related to Cp. So del S by del T at constant pressure, that you can write in terms of Cp. Cp by T actually, right? Cp was T times this del S by del T at constant pressure. Okay. So we have this first equation, we have this second equation. Okay. We also have one Maxwell equation. Which Maxwell equation? Del S by del P at constant temperature is equal to minus del V by del T at constant pressure. Okay, this is one of the Maxwell equation. Hello.
Yes, sir.
Okay.
Yes, sir.
So this second term of the first equation, that can be tackled using this Maxwell equation. So here we have P by S at constant T, and in Maxwell equation we have S by P at constant temperature. It is just reciprocal of that, right? Correct. What we need? We need del P by del S at constant temperature for the second term of the first equation. So that we can write 1 by 1 divided by this whole thing, right?
Negative.
Negative sign. Okay, so this, let us say it is third equation. Okay, so we just need to substitute this second equation for this third term here.
Yes.
Okay, we can substitute this second equation for this third term, and we can substitute this third equation for the second term. Okay, so what we have now? फर्स्ट टर्म वैसा का वैसे ही रहेगा dp del t by del p at constant s, and this will be -1 divided by del v by del t at constant p, and del s by del t by p की जगह cp by t is equal to -1. Okay, correct.
Yes, sir.
And what we had to find, actually we had to find del p by p at constant s. Okay, so we need only the first term, we need only this term, first term. Okay, so you can bring everything on other side, so we will be left with del p by del p at constant s. This will be equal to, bring everything on another side, so this negative and negative they will cancel out, so we will be left with t by cp, and this denominator will become numerator there, so del v by del t at constant. Okay,
Yes, sir.
fine.
Yes, sir.
And now see, everything is in measurable, but we can also use the expression for compressibility, sorry, thermal expansion coefficient, that was beta is equal to 1 by v del v by del t at constant pressure. Okay, so del v by del t at constant pressure, this we can write beta times v. Okay,
Yes, sir.
correct. So this equation becomes del t by del p is equal to t by cp times beta v. That's it. Okay. Okay.
Yes, sir.
So that's what we got. Now, if we do the same thing using Jacobians, so what we were asked to write del t by del s at constant del t by del p at constant s.
Yes.
constant S. So first of all, let's write this in terms of Jacobian. So what it will become? T by P and S will be repeated. Okay.
Yes, sir.
Now entropy is coming with what? It is coming with temperature in the numerator,
Yes.
right? So then what can we use? You can use the Maxwell equation. Okay.
Yes. Yes.
So T comma S is P comma V. That's is the Maxwell equation, right?
Yes, sir.
Divided by P comma S. Okay.
Yes.
Hello.
Yes, sir.
And
Correct.
if P and S were coming together, then what we had to use?
CP. CP by T T comma P.
If S and P they are coming together, then we'll have to use Cp by T,
T comma
T comma P. Okay. So can we write this thing is equal to T by Cp and P comma T, and this was already there, P comma V. Is it okay?
P. Yes, sir.
Right? We have used the expression for Cp in terms of Jacobian. Okay.
Yes, sir. So we got the same.
Now P is repeated. P is repeated. We can also flip the sign once. So
Yes.
it will be V comma P divided by T comma P. So P is repeated. P is repeated. That means it is constant. And we have to take the derivative of with respect to T.
The V by 2
Right? So we will reach there. Okay. So that's what we have got. Okay. So this not here. Actually, this thing we have already got. Okay. So we came to here. But if again you want to use the expression for beta, that also you can use. Okay, that also you can use. It was 1 by V, and it was thermal expansion coefficient. So V by T at constant P. Okay,
Yes, sir.
right?
Yeah.
So what we have this particular thing, T comma P by, sorry, V comma P divided by T comma P. This is what? This is beta times V. Okay. So what we had? We have now we had to write this thing, and we have got T beta V by Cp. Okay. So
Yeah.
I think the second method using Jacobian, it is more easy, and we don't need to worry about where to start with. For example, we started with cyclic properties. Okay, cyclic relation. But
Yes, sir.
how do we know that we had to start with cyclic relation? So maybe we can start using some other relation. Okay. Then if you use some other relation, then maybe there can be some increase in number of steps. Okay. But anyway, we'll ultimately reach to this particular equation. Okay. But if you use the Jacobian, then we have a proper algorithm. Very simple algorithm. First, write everything in terms of Jacobian. If entropy is coming with T, then use the Maxwell equation. If entropy is coming with P, then use the Cp. Okay. And you get the final answer. Okay. And if you want to condense it further, you can use the definition for alpha and beta. Okay.
Yes, sir.
Okay. So I hopefully it is clear. Okay.
Yes, sir. Yes, sir. This is much easier,
Simple.
and number of steps are drastically
Number
reduced.
of steps are fine. Maybe sometimes this classical methods can be easier, but here we have a algorithm. Okay. We have proper instructions that how we need to follow. We need to proceed. Okay. Write everything in terms of Jacobian, and then check whether entropy is coming with which variable, whether temperature, volume, or pressure. Then you use the particular relation. Okay. And that's it. Only 2 3 steps. Okay.
Yes.
Let's do one more question. Okay. Then it will be more clear. You know Joule-Thomson coefficient. So I'm doing this question so that we can also discuss Joule-Thomson coefficient. Joule-Thomson coefficient mu is del T by del P during a throttling process or isenthalpic process. Okay, that is the Joule-Thomson coefficient. Okay,
Yes, sir.
and we are asked to write, or we are asked to prove that mu is equal to P by Cp P beta minus 1. And without Jacobian also you can do, and using Jacobian also you can do.
T, comma, H.
There will be some more steps, but you can ultimately do it. Okay, so that is not too difficult. But if you, but things are clear. Okay, we know that first we need to write everything in terms of Jacobian. Okay, we will start with this thing. We will write this thing in terms of Jacobian. Now, what we have this H. Okay, let's write a few steps so it will become clear. We have del T by T at constant enthalpy, so it will be T by P, and H will be repeated. Okay. Okay. Now you have this H. We discussed that if any potential comes, then we can use the expression for potential. Expression for potential was dH equal to dH equal to T ds. Okay, T ds plus V dP.
dP.
Okay.
P comma D. Yes.
So like that we can do. Okay, but we have H comma T. Okay, we have H comma T. Here what we have? We have H comma T, no?
Yes, sir.
H comma T and H comma P. So once you will write W is equal to T, and once you will write W is equal to P. Okay. Fine.
Yes, comma T.
Let's write it H comma T. So in the place of W you will write T. So T S and W की जगह T plus V P और W की जगह T. Okay. Similarly H comma T or H comma W or W की जगह P. This will be T S comma P plus V P comma P. Right? And we discussed that if any of the index is repeated,
it will become TS.
No, zero.
TS comma P.
So it is TS comma P. Okay. So now this Joule-Thomson coefficient, this will become what? T comma H. So what is T comma H? It is T S comma T plus V P comma T divided by T S comma P. Right?
Yes, sir.
And you can write it one by one as well. So it will be T S comma T. No, T will cancel out, right?
Yeah, for first part it will
For the first term, it will be cancelled out. Okay, plus V by T, T comma T divided by S comma P. Okay.
Yes, sir.
Now,
Repeated
now,
term first. There is repeated S and repeated P in first term.
Repeated P. But we had to write in terms of what? In terms of coefficient. So we will use the definition of coefficient. So as it's coming with P, okay, as it's coming with P, so we'll use CP relation, and
S is coming with P.
Again here also it is coming with P, so we'll use the CP relation. So we'll be left with mu is equal to, and here S is coming with T, so we'll use the Maxwell equation. Okay. Right?
Yes, sir.
Okay. So S comma T, this will become V comma P from the Maxwell equation, and it is divided by S comma P. So it will be Cp and T comma P divided by T. Okay. plus V by T, and this PT is PT, okay, fine. And again, S comma P, so we can use the definition of CP. So it will be CP, T comma T, sorry, divided by T, okay.
TT cancels.
So this T and T, they will cancel out. So we will be left with T by CP, V comma P, T comma P,
P comma
plus V,
P comma
and let us flip the sign. So T comma P, so we will get a negative sign there, and T comma P. Okay, so now it is, I mean, T and T, they are at the same place. Okay, fine.
Yes.
So they will cancel out, right? Minus V,
Yes.
correct?
Yes, sir.
And there was one more CP. One more CP was there. Okay, so CP we can take common. So we will left with T V comma P and T V comma P minus V. Okay, hello.
Yes, sir.
Ah. And what else?
P
Ah,
comma
we
P.
now we can use this thing.
So you write to
This particular thing. This was used in beta, right?
P comma P.
It was used in beta, right? What was beta? Beta was 1 by V,
P.
P comma
So we
P,
get to T.
T comma P. यही था ना?
Uh,
So this particular thing will be beta V, correct?
yes, sir.
So mu is our 1 by Cp, T, and beta V minus V. And V again you can take common. So it will be V by Cp, T beta minus 1. Okay.
Yes, sir.
So this is Joule-Thomson coefficient in terms of specific volume, specific heat at constant pressure, temperature, beta, in these terms. Okay.
Beta. Yes. Yeah. Yes, sir.
So if you know the coefficient of thermal expansion, that is beta, if you know specific volume, if you know specific heat at constant pressure, then you can calculate the Joule-Thomson coefficient. Okay.
Yes, sir.
And what is Joule-Thomson coefficient? Where I mean, what is where it is used?
It's along the lines and for the throttle valves.
Along the throttle valves. And where we use throttling in refrigeration we use, right?
Yes, sir. To reduce the pressure.
Okay. So actually P and P, and we have some. We can make isenthalpic lines, okay? Because this is the isenthalpic process, okay? So during throttling, pressure will be reduced, okay? So let
Yes,
us
sir.
say we have this particular throttle valve, okay? We have this particular throttle valve, and a gas is entered here. So this is 0.1, okay? Gas is entered here, and it is coming out from this point. This is 0.2, okay? So this is 0.1 and this is 0.2, okay? 0.2 can be here also. 0.2 can be here also, 0.2 can be here also. It can be anywhere depending on the amount of throttling you are doing. Okay, how much pressure is dropping? Okay, so proper pressure is dropping. That means you are coming this side. Okay, so initially you can see if you are reducing the pressure, then temperature is increasing, not decreasing. It is increasing. Okay, hello.
Yeah, and after a certain state,
After yes, after this particular maxima, if you further reduce that pressure, the temperature is reducing. Okay, so you are getting a cooling effect. Okay, so basically you have to cross this maximum. Okay, so you can make many isenthalpic lines. So this is, let us say, at any particular amount of enthalpy, this is H1, let us say. You can make more such lines. Okay, like that, sorry. and you can join these points of maximum values. Okay. Okay, these maxima points are basically called inversion points. Okay, these maxima points are called inversion points, and this line that joins all these inversion points, that is called inversion line. Okay, so if you are doing throttling on the right side of inversion line, then you will not get cooling effect. Okay, by throttling you will be basically increasing the temperature, not reducing the temperature. Okay, so if you want to get the this cooling effect, you will have to be on the left side of this inversion line. Okay,
Yes,
so
sir.
if someone asks that during throttling will temperature always increase, sorry, always
No,
reduce, answer is
no.
no. We have to be on the left side of this inversion line.
Yes, sir.
Okay, and the slope
Sir,
of
there
these
is a
lines are basic.
I have a question regarding this. So for this inversion line, not inversion line, isenthalpic lines, it also happens in the normal lines, right? Feed lines or the or normal lines which is used for transfer of the gases. And in a particular case, I saw that due to Joule-Thomson effect only, either I don't know whether it is hydrogen or oxygen. There was this due to the rapid decrease in the and increase in the flow and decrease in the pressure, and there was rapid rise in the temperature, and it reaches the ignition temperature, causing the accidents. I think it is for oxygen, I guess, or
It can
hydrogen.
happen. Like, okay, so there are certain gases. Okay, one more thing I want to discuss, that along this inversion line where it intersects this particular thing, this is called maximum inversion temperature. Okay, maximum inversion temperature. Okay, so if you want to get the cooling effect, then you will have to blow this inversion temperature so that you can be in this region, right? You can be in this region.
Yes, sir.
Okay, but certain gases, they have very low inversion temperature. For example, hydrogen. For hydrogen, this maximum inversion temperature is approximately, I don't remember, it is approximately minus 68 degrees Celsius or something like that. Okay, so if
Yes, sir.
you want to get the same cooling effect for hydrogen also, then you first need to cool it down below minus 68 degree only. Only then you will able to get this cooling effect for hydrogen using throttling. But if you are above this temperature, then what will happen? Because of
Always
throttling,
increase the
as you
temperature.
are saying that there can be some sudden, restriction, or there can be like there is some flow that is going on
Friction.
peacefully, but there is something which is disturbing it. Okay, like something like throttling. Okay, any disturbance that can act as a throttle valve. Okay, so as the result of that throttling or sudden disturbance, that can increase the temperature. Okay, so as you are saying that it can happen, so yes, it can increase temperature.
And sir, the temperature, can it reach it that activation temperature, the
It
temperature
depends
needed for
on
the.
what, yes, it depends on what is the ignition temperature of that particular thing. For hydrogen, the auto ignition temperature is quite high, higher than diesel, higher than gasoline.
Yes, sir.
And also depends what is the mixture. Okay, like if you have only fuel, then it will not burn. You also need to have some oxygen. You need
Some
to have the
oxidizer,
fuel air
yes.
mixture, and not just fuel air mixture. It should be within the flammability limit. Okay, if it is
Yeah,
outside the
nearby.
flammability limit, then it will not,
Okay.
ignite. And also yes, hydrogen had quite wide flammability limit. Okay,
Flammability,
so
it
starting from
easily
very lean to very rich, it can
very
burn.
rich. Yes.
But anyways, so this is your Joule-Thomson effect, and the slope of these lines, asymptotic lines, that is your Joule-Thomson coefficient. And this slope, you can see it can be positive, it can be negative, or it can be zero. Okay, so on the right hand side of this inversion line, this slope is negative,
Po-
and
uh,
on the left hand
Negative,
side it is
positive.
positive, and along the inversion line it is zero. Okay,
Yes, sir.
Similarly, we have one more equation like this Joule-Thomson coefficient relation. There is one more relation that is called Mayer's relation.
Mayer's relation. Okay.
So Mayer's relation is basically Cp minus Cv is equal to TV
Yes.
beta square by alpha. Okay, for ideal gas it is R, right? But for
Yes, sir.
in general it is like this. So if we are asked to prove this, then again we can use the same concepts that we have used earlier, that we have just discussed. Okay, and we can prove it. So I'm not doing it here. You can try to prove it yourself. Okay.
Yes,
In
sir.
the books, the proof is given using this our partial derivative, the classical methods, but you can uh, try to do it using Jacobians. Okay.
Yes, sir.
Okay. So what will we do? First, we will write everything in terms of Jacobian. How will we write in terms of Jacobian? We have the Jacobian expression for Cp. We have the Jacobian expression for Cv.
See,
Okay. We have the Jacobians for you know
beta.
each other terms. Okay. So
Yes.
you just write everything in Jacobian and do some manipulations using the properties of Jacobian, and you can prove that very easily. Not difficult. Okay.
Yes.
It is like 2-3 steps. Okay. So I'm not doing here. You can do it. It's very easy. If you find any difficulty, then we can we can discuss that in the next lecture. Okay.
Sure, sir.
So I hope that this Jacobian stuff is clear. Okay. And you don't need to
Yes, sir.
memorize that square or something like that.
Yes, sir.
So the four Maxwell equations, they are just condensed to one particular equation, Ts is equal to Vp. Okay. I think it is easier than that circle or square, whatever. Okay.
Yes, sir.
We have few more questions that we can try to solve, but one more important thing that we should discuss here is that is Clapeyron equation. Okay.
Yes, sir.
So you have any doubt in Clapeyron that we can discuss? Otherwise, we will just write it. You know
Yes,
what
sir.
is
It is clear in the lectures.
uh,
Clapeyron equation used for the phase diagram.
and why it is important? Because phase change takes place, all the time. Especially in the combustion, you have the liquid fuels, then there will be evaporation, right? Then it will get mixed with the air, then the combustion will follow. Okay,
Yes, sir.
so it is
Uh,
quite droplet evaporation. Yes,
no, no, sir, nothing.
and what is Clapeyron equation? It is basically a relation between temperature and pressure during phase change, or you can say the saturation pressure and saturation temperature. Okay,
Yes, sir.
so I will just write that. What is Clapeyron equation? Clapeyron equation is used for this.
Saturation is equal to Hg minus
And
Hg.
there is one more equation that is basically more simplified, or special case, that is called Clapeyron-Clausius equation. You know that?
Yes, sir. It is using approximations. And
Approximation, yes. Approximation is
yeah,
that for
your
very for very small
specific volume of gas is
for
very
very small
high.
temperature changes, the latent heat of vaporization you can consider to be constant. And also you can use the ideal gas equation. Not can, you'll have to use the ideal gas equation, and then you'll get the simplified version. So that simplified version is basically this log of P2 by P1 is equal to latent heat of vaporization, that H of F means fluid and G means gas, divided by R, your gas constant, divided by T1 minus T2. Okay,
Yes, sir.
we have used two approximations. One is ideal gas, and another is
Vf
small.
Vg is equal to 0. Vf is equal
Uh,
to negligible. Vf
uh,
specific volume of the uh, liquid is very uh, less compared to the specific volume of the gas.
no, actually, we are coming from this particular equation that we have already used, that you are saying dp by dt at saturation, that is given by HFG.
T
What else?
into T into
What else?
T into VF minus VG.
No. HFG V FG divided by what else?
Uh, RT
Huh? T
T into Vg minus Vf. It was Hg minus Hf by T into Vg minus Vf.
what was that? Repeat. I will try.
Yes, sir.
Hello?
dP by dt saturation
dP
is
by
equal
dt.
to
Uh,
Hg minus Hf by
H F Hg minus HF
by T
by
into Vg minus Vf.
P into
Vg
so
minus
V.
Vf.
And that is in the denominator or numerator?
Denominator.
V is in the denominator.
Denominator. Vg minus Vf. Yes, sir.
Yes.
So in this approximation, the Vg was supposed to be very higher than Vf, so it was only Vg, and then Vg we get it from the ideal gas equation. So Clausius.
And what about this latent heat?
It is as such, sir.
As such, but there are two temperatures, T1 and T2. So at which actually this latent heat of vaporization that also changes with temperature. So which one we have to use?
Gas.
No, I mean for gas also, like not gas. This is phase change relation. So this is latent heat of vaporization. Okay, and the latent heat of vaporization, that will be the function of temperature.
Yes, sir.
Okay, so there are one more approximation, that is that H and Fg, that can be considered to be constant for small temperature changes. Okay, so this change in temperature should not be very high.
Very, very. Okay. So it is constant.
So there are some questions we could not solve the questions because I wanted to discuss this Jacobian, because it is not usually discussed for
Sir,
engineering.
will you be sharing these questions, sir?
I
I
will
will
share
try
the whole
to.
PPT. I will share the whole PPT, this PDF. Okay.
Yes, sir.
You know how to access that? You go to Swam portal. There will be what is it? Problem solving sessions like that. If you click there, you will get one Google spreadsheet. In the Google spreadsheet, you will get for the link for these PDFs for the YouTube
The link,
recording.
yes, sir. The link was there only for YouTube, sir, not for the
No, no,
PDF.
it is. I mean, it is for all that. Okay.
Okay, okay, sir. I'll go through it.
Actually, there is link for Google Drive folder. Okay, so if you go to Google Drive folder, you can find all these PDFs.
Okay, sir. It will be helpful.
I don't think we have much time, but let us try to solve this question.
Yes, sir.
It is saying that equation of state for a real gas is given by P is equal to
T
RT V by
T
V
minus A
minus A by V square. Okay, then it is saying that we have to find this partial derivative. Del P by del T at constant V. That we can easily find del P by del T at constant V. So the first term we are trying to find with respect to T. Okay, so it will be R V by B because
T
it is
minus B.
V is constant. Then the second term will be 0 because there is no T
0.
there. Okay, fine. We got that. Required to evaluate the related Maxwell equation. So where it is used, del P by del T at constant V. In some Maxwell equation it will be used, but we can, yes, wherever it is used, we can use this particular value. Okay. Then consider the gas at the same gas at 300 Kelvin at 0.86 meter cube per kg. Okay. So T is given and
B is
specific volume.
point. Yes, sir.
Okay. Then it is saying that state of air. Air means basically this gas. State of gas changes from this 300 Kelvin to 302 Kelvin. Okay, so this is
Delta
T2,
T is given.
and V2 is also given 0.87 meter cube per kg. Okay, fine. Because of some disturbance, we have to estimate the change in the pressure of this gas. So we can find that change, right?
Yes, sir.
What will the change in pressure?
Delta P is equal to delta T into R by V minus V.
Pressure, here what is changing? First of all, let us see that. What is changing? Here temperature and volume is changing, right?
Yes, sir. Both are changing.
Both are changing. So pressure, let us say, is the function of what is changing? Temperature and volume is changing. So change in pressure will be del P by del
By
T
T at
and
V
that constant
plus
V plus del P by del
del
T at constant
at constant.
C. Right? Okay. Fine. So del P by del T at constant V, del P by del T at constant V, we will get got this from this particular thing, right?
Yes, sir.
Okay.
R
And
by
del P by del V at constant T, that we can also calculate from this their equation.
relation.
Okay. From this relation, and we just need to substitute these values. Okay. dt, what will be dt? Dt will be T2 minus T1. And see, when we say dt, it basically means it should be very small.
Very,
Okay,
very
so
small. Yeah.
very, very small, and here it is quite small. Okay, so here it is quite
Yes.
small. It is 2 Kelvin. So we can consider this to be small, not infinitesimally small, but still quite
Small.
small. I mean, significantly small. And dv will be v2 by v1. Okay, so we have this dt and dt, and this derivatives you can calculate from this particular equation, and you just substitute the values, and you will get the change in pressure. Okay.
Yes.
And another part is saying estimate the change in pressure of gas. Okay,
Gas.
that
dt.
we will calculate. It is saying to compare the result if the gas was an ideal gas. So for ideal gas, we will have this PV is equal to RT, right?
Equal to RT.
So instead of this particular ideal gas equation, we will use this real.
We have
Sorry,
to check it with the
instead
ideal
of
gas
this real
equation.
gas equation, we will replace with the ideal gas equation, and you can calculate, and we can check how much is the change. Okay.
Yes.
Okay. Now coming to the next question, it is saying on a PV diagram for a pure substance, the slope of isotherm evaluated as dP by dV at constant temperature is strictly negative in the both single phase region and two phase liquid region. And
False.
I think it is true and false. Okay.
It is false.
True and false. You are saying it is false.
Yes,
False.
sir. In two phase, it is.
It is a straight line, parallel straight line. So this will be zero, no?
Yes, sir. Straight line. Yeah.
So here it is del P by del V
Del V is equal to 0.
is zero. Here it is negative. So number 7, it is saying PT phase diagram. Explain why the slope of all constant volume lines passing through the two phase region at a specific temperature are equal, allowing the slope to be represented by its ordinary differential dV by dt at saturation. So that you are telling that it is not the function of the specific volume, right?
Yes, sir.
That
With the
discussion
look.
comes when we discuss the Clapeyron equation. Now, question number 8, it is saying the Clapeyron equation evaluates the property change accompanying a phase change, right? Which of the four fundamental equations serves as the direct mathematical starting point for driving the Clapeyron equation? So, for Clapeyron equation, we had dP by dt at
dV by
saturation.
dt saturated is equal to.
But which Maxwell equation we used?
Yes, sir.
Did we use any Maxwell equation?
Sir, can you repeat?
So we have to calculate this particular dP by dt at saturation. So it is coming in the second part, right? In the B.
Yes, sir. Yeah, it is there. dV by dt saturation is equal
Uh,
to dou P by
uh, and it is independent of specific volume. So it will become by dt,
dou T. And
right?
yes, sir.
And this second term, I mean, this is ds by del T at T.
Is equal to
This becomes what? For this we use, we don't want entropy anymore, so we will use ds. ds will be ds plus dp. And if you fix the temperature, then pressure change will be zero, right?
0.
So ds is equal to TDS. So
ds by dou U is equal to
ds you can integrate will be dh by T expanding the circuit. Entropy change from gas to gas, gas to gas, like that. Okay, and temperature is constant. You can take it out because it is saturation temperature. I'm
constant.
not writing about it. You can find it in the book and like that.
Yes, sir.
So already we are running out of time. So there are a few more questions. I think most of the thing we have discussed, and these questions can be solved based on the discussion.
Yes, sir. I'll try to do this, and if any doubts are there, we can ask you in the next.
In the next session. So, and we also had to discuss one more thing, but again, we have to reserve for the next session. In the previous session, we had someone had doubt in the second law efficiency, and even I had some doubt
Yes,
because
sir.
in the lecture it was explained something else, and we solved our questions using some other concept, and we said that probably in the lecture some other definition might have been used in some other method.
Efficiency for the yes, sir. It was about
Okay.
efficiency only.
So in the lecture, it was derived explicitly for heat transfer type of devices without any work effort. But it is very important to note that what definition we are using. Okay. So I will just read one line and we can do it in the next session if required. Okay. So there are some definitions of second law efficiency, and this is from Sinjal. Okay. So this
Sanjay.
single book. Okay, so it is this also saying that the definitions above for the second law efficiency do not apply to the devices that are not intended to produce or consume work. Okay, so which type of devices you are working with, according to that your definition will
Efficiency.
change. Okay, so it is also saying therefore we need a more general definition. However, there is some disagreement on a general definition of second law efficiency. Okay,
Efficiency.
thus a person may encounter different definitions for the same device. Okay, so even if you have same device, so one person can use some other definition, another person can use some other definition, and both of them can find different answers. Okay, it depends which definition we are using. So according to that, our answer will change. Okay,
Yes.
so if someone had more doubt in this second law efficiency, then we can uh, discuss more definitions which are used. But for the time being, I think we should stop here. We are already running out of time.
Yes, sir.
So thank you for joining. Try to
Thank you,
solve
sir.
these questions. If you get any difficulty, we will discuss on the next session. Okay?
Sure, sir.
Good night.
Good night, sir.